Hello. I didn't know I was live. Am I actually live? Wow. Okay. That's you bring out the title. Yeah, that's okay, the title's there now. Thank you, everybody. I didn't realize I was actually live, so that's great. Okay. All right, click refresh. I edit the title. You guys are so funny. Okay, let me change this. Oh, I can't change latency. That's okay. Um, let's see. Save that. Nice. Okay. Should be good. Should be good. I'm actually not gonna be here for the first part of it. Hey, Nick, I'm glad you're here. Yeah, I said really fast. I'm not gonna be here for the first part of it. I have a few things to do. And let's be honest, Tesla's gonna be late anyway. But I figure this is a cool place we can hang out. And wait, is there a thumbnail? What's the thumbnail? What the heck? I'll try it down here. Upload thumbnail. It's probably just like my face. It probably looks so stupid. Hold on. There. Save. Okay. Nothing. I was just setting up the stream, so it should start in 7 minutes, but Tesla's always late, so I'm sure it'll be late. Okay. Yeah, I type like 130-ish words per minute. A little more, maybe. A little less if I'm tired. So, hang out, chat. Oh, no loud noises for you. Hang out, chat. I'll be back in a bit. I'll be talking on the text, but let people know. Let me make this full screen for you. Oh, I can't. Well, you can watch it live yourself. This is more. Yeah, the stream link is in the description. Check the video description for the stream link. I can also just paste it here for you. There you go. So F11 that boy. So yeah, you can watch the stream live, but use this to chat. I figured it would be cool, or we can watch together, and then after it's done, we can talk and hang out. With that. So. Okay, so I'll put that. I can pin this actually, which is really nice. So I'll pin that message so everybody sees that. Cool. All right, hang out, talk. I'm so excited. I don't know. I'm kind of like not that excited because I'm like, they can't show us that much. But all right, I'll be back in a bit. I got a couple things to do, and then I will be joining you. You might have to refresh because I edited the description after I went live. Yeah. Oh, that's not right. Don't. Not that. Okay, there. Now it's in the description. Yeah, so it's in the description now. So you might have to refresh to get that. So, all right, be back in a minute, or more than a minute. And you know what? I should just not leave this on. That's kind of stupid.
I'm not the man you want. You've made a mistake.
I'm in touch with technological advances pretty well everywhere, and I can tell you that no one has produced anything like this.
Good thing my camera and microphone are off. Just kidding, just kidding. How is my talking? Oh, here. Get the other light too. How is my talking versus the music? I'm sure the music is like blasting your face off. Let me know how that does. I don't really have much to say. Oh, thank you, Eric. I'm glad you liked the Powerwall video. Oh, Lucascraft, thank you so much. Should be in this event for helping with the AI better. Oh, voice is still too low. Here, hold on. There you go. How's that? Oh, uh-oh. I messed it all up. Okay. Oh, every time the music stops, it gets me. Yeah, I'm glad you guys enjoyed the Powerwall video. Thank you so much. Because when I do things that aren't self-driving now, dishwasher stream, you know, some of the subscribers, of course, don't care because they subscribe for full self-driving, but also YouTube does not push it as much. So when you watch those videos that are not full self-driving, it helps me like a ton. So thank you, thank you, thank you. I appreciate it. It was supposed to start 31 minutes ago, but you know what? This is nothing, nothing new for Tesla here. Oh, Eric, you emailed me, right? Yeah, we were talking on email or Twitter DM. I've been talking to a lot of people about their solar and power walls and their potential systems. So thank you, Essential Roads. Appreciate it. Turn down the music. Okay. What can I... There. Can I have it, like, super quiet? How's that? Yeah, I did. Hey, calm it down with your spam. All right, that's enough. That's enough of the... Oh. Oh, what did that do? Uh-oh. Yeah, if you really need to see my face, I guess. Like, who cares what I look like? Turn up the music. Get out of here. Oh, thank you guys for, yeah, liking that Powerwall video. I appreciate that. That's great. I'm glad. Turn on slow mode. Move your face cam up. Get out of here. How do they only have 30,000 viewers? Yeah, it'll jump up once it starts, I'm sure. I can try to turn on. Oh, what is that? Oh, I like that better. Oh, somebody. Oh, Adrian, keep the music on. Okay, fine. It's not my music, it's Tesla's music. Turn on slow mode. Okay, I'll try. To be honest, this stream, I didn't mean for the stream to start. I was trying to get it set up, and then it's like, you're live now, and I was like, oh, okay, great. That's great. Let's see. I don't know if I can turn that stuff on. Oh, here we go. There we go. There. I got a slow mode for you. I just got 10 seconds. 10 should be enough. We don't have that many people here, so. Robert Wendell, thank you so much. Appreciate that. Yeah, oh my gosh, do not compare it to the Model Y delivery. That was terrible. I remember I stayed up for that, and thank you for suggesting it, Nick. I stayed up for Model Y, and it was like the most boring event. I don't know what I expected. We all knew what the Model Y was, and what are they going to show us, but that was terrible. Slow mode has no effect on me. Yeah, you're immune. Oh, Heidi, thank you so much. Appreciate you guys. That's nice. I want to see it. Good job, Nick. Thank you. Thanks, Mike. I'm glad you're liking it. No, Epic Benjo, about an invite. I couldn't have gone if I was invited anyway, but some of the beta testers asked, like, hey, could we get invited? And Tesla said no. They're like, we're full. There's too many people here, so I can't start it. What if I could? Ronnie, oh, you guys are killing it. Thank you so much. Thomas, binging my videos. I appreciate it. That's great. Tonight we're obviously getting 6-legged robots. Right? That's what the crazy fan. I have no idea what to expect, and like every event, I'm worried that people are gonna be, let down. You love my Twitter account? Well, thank you. That's funny. I don't know if I've ever heard that. Oh, he turned it down. Could you have taken his place? They were not full, Nick. They lied to us. Michael, did I ever resolve my dirt in the rear bumper issue? Nope, I got a new car. But I will be taking the bottom off of off the Model Y. Here, I'll make this a little bigger. I will be taking the bottom off the Model Y in a few months, and we'll see if that's full of dirt. My wife heard you say my name and thought Elon Musk was giving me a shout. That's so funny. No, just some random guy. No Elon Musk. Oh, invites are tied to the person. Darn. That would have been awesome. KR. Thanks to me. Thanks to you, KR. I really appreciate that. Wow, you guys are so cool tonight. Tesla, keep delaying. Don't start yet. I'm gonna text Elon. Yeah, right. That's so funny. Oh, thank you, Dion. You guys are so nice. I appreciate it. I'm glad you guys like this stuff. It's funny because to be honest, I get lots of, nice comments and Thomas Valley towards the Cybertruck. All right, it's going there. Thank you. I appreciate that. I do get a lot of positive comments, which is great, but man, only 1 or 2 of those negative comments really gets to you. And I'm like, why? Like, be nice to me. Please don't type in chat unless you're a big Tesla investor to plus shares. Too bad I can't link up the chat to your brokerage account, and only if you have calls or shares. That's the only way you can chat. Are people asking you about? That's so funny. What did he ask you? I gotta find this. Oh, I can't find it. Chat's going too fast, even with the 10 seconds. All right, no look comments. That's creepy. More Cybertruck info would be appreciated. Oh, thanks. I'll remove the pin. There you go. Maybe I should keep the... I'll keep that up, though. There. I'll pin the official live stream in case anyone wants to watch it. Because there will, of course, if you watch mine, I'll keep it up. And I'll try not to talk too much while it's going on, but there will be a delay. So some people might want to watch it live, but chat here, which would be good. Dirty Tesla from your OnlyFans site. No. Oh my gosh, it's so funny. What do you think the exploded image for AI means? I have no idea. I don't know anything about that, to be totally honest. That's way above me. Why am I called Dirty Tesla? Because I live on a dirt road and my car is always dirty. Always dirty. And it's the first thing, people are like, why is your car so dirty? So I was like, you know what? I'm just going to name the channel Dirty Tesla. So before they even see anything, they know that my car's dirty. What time is it starting? It is starting 38 minutes ago. That's what time it's starting. Oh, I know, Brendan. Everything is delayed. I just saw Toyota is cutting production by 40% because of the chip shortage. What? 40%? Oh, here we go. Full self-driving. This is mine. Oh my gosh, they took this from my video. Just kidding. Oh, dude, they're showing that weird creep. That's so funny. This is how it acts, yeah, with the weird little... They're not... Oh, this is cool. Oh, I'm so glad they're showing full self-driving stuff. I was worried we weren't going to talk about full... Look at, they show that weirdness. That to me is very strange for it to do that. Oh, yeah. Look how slow it goes to the intersection. Oh, they're showing the real thing. That's for dang sure. Oh, that was good. I'd be scared, but... Who is this? Is this Omar? They took this style from my videos. Just saying. Oh, going around that guy, going around the car. Oh, destination. That's the destination. Sweet. Park. Oh, let's see. He's gonna. Is it the same video? No, it's a different one, right? I wasn't paying attention that much to the beginning of it. Yeah, it's a different one. Okay. Sweet. That hand placement is weird. They obviously have their confirmations off. You can tell for this person they don't have to have their hand on the wheel. Man, I want that so bad. I don't blame them. Oh, okay. This is the same video. My bad. Nick, shut up. Yeah, it's the same video. Yeah, so that guy's got confirmations off, it looks like. Unless he's... Oh, no. Maybe... I don't know. Can you guys tell? Is he kind of tugging on the wheel just a little bit? It looks like maybe... Oh, don't do that. It looks like... I don't think so. Yeah, I think he's got his confirmations off. I want that so bad. Dude, Epic Benjo, they better not be showing a better version. I hope they would give us the best... Why would they give us a crappy version? Cool. Yeah, this is sweet. Maybe I just need to trust it more. That's actually, yeah, they need to kill confirmation of the cabin camera. I totally agree. What does it say? What was I going to say? The light finger drag for confirmations. Oh, I always still grab on. I can't help it. Yeah, Bill, we got grid. The grid is operational right now. Yep. I'm getting older here. Yeah, we're all getting older. I'm glad they gave us this video to watch, though. They should have used one of mine or one of the other beta testers. That would have been so funny. Like, that stop is so bad. Oh, that's what I was going to say. Yeah, close your eyes. I don't think so. In the email that they send us when they send an update, one of the bullet points is like, make sure you're clear to people on why you're intervening. And like, so they're like, we see that often, not me specifically, but to the beta testers, you're taking over even if you didn't really need to. Like, the car was going to do the right thing, but you still took over anyway. So you should let people, and they're like, that's totally fine. You do that as much as you want, but let people know why you're doing that and that you took over kind of just for your own sake. Because I don't know, like, I totally agree. So maybe I should trust it a little more. It's hard though. Dude, zero disengagement so far. This guy's been driving for like 20 minutes already. Isn't this impressive? It's not looping at all. That's a cool little loop. That's actually a good idea. Oh, they did this must be waypoints. No. I don't know how they did it. They probably got some special software. Oh, and look. Okay. Look at Nick. You see this? So this right here, do you see my mouse? Oh, you don't see my mouse, do you? Oh, that's lame. What if I make it not full screen? Okay. I'm going to make it full screen. Okay, I have to make it full screen. Okay, look at the top where it says Tesla for the user profile. Oh, you do see my mouse. Look to the left. See, this is our little report button. And then this special, there's another icon here to the left. That's a steering wheel icon. I don't know what it's for, but it's like a developer version of the car that I don't have. So we back Tesla. Change your name. Your name is changed now. You would think they would have more footage for us to watch. Yeah, it's on, they do. They have lots of footage. It's youtube.com/c/dirtytesla. There is hours of beta footage for you to watch. No, yeah, he's looping. You're right. He's going in a loop with 0 disengagements. This is insane. Yeah, Robert, I agree with you. It's super annoying. Like, why would they tell us 8 and then take this long? Like, I'd say like 15, maybe 20 minutes late. That's still kind of rude, but like, come on, dude. Just tell us it's at 9. Like, the left hand seems fake. No, it doesn't. No, the video's not looping. This guy's been doing full self-driving for like 2 hours straight, 0 disengagements. Look how good it is. This is it. I'm just joking around, guys. I know the video's looping. No, those are the girls' twins. Oh my god, dude. I'm hiding that. Don't say that. Why are you guys saying these things? I'm just blocking all your messages, so don't do that. That's so funny. Look at his finger, it looks fake. What? The way his fingers kind of move, it's sliding, it's kind of weird. This is a live feed. Yeah, this is live. Right, this is AI day. This is AI day right here. Where do we get the fake arm? He has too many fingers. That's really weird. I'm gonna try driving like that. I find it very strange. But again, he doesn't have to have his hand on the wheel. He doesn't have to do those confirmations like I do. So he's got a much better experience. I wish they would turn that off. Like, I don't blame him for keeping it on, but oh my gosh. Thank you, Eric Lee. Appreciate that. I would assume this is the version we're on. I don't think, like, obviously there's other versions that we don't have yet, the beta testers, but they're not going to have a version that's clearly better and not give it to us. Like, obviously, they want us to have the best version, I would hope. I did hear there's some either theories, I don't know if it's confirmed or whatever, but that they tune things sometimes. Dude, stop. They tune... I'm sorry. They tune things so that it was phrased like more aggressive or something, where it is more likely to make mistakes so that they get those interventions and kind of get the data back. And they could, theoretically, they could tune things a little more conservatively so that we wouldn't need to disengage more and all this stuff. But then they wouldn't get as much data. So for the public release, you would get... they would like tune it down a little bit. So if you all donated $1,000, I could buy a Model S Plaid. Yes, I could. This is all a simulation. We are definitely on Elon time here. Has he tweeted anything? Have you guys looked? Oh, okay, here we go.
Thanks for coming.
I'll be quiet.
And sorry, I had some technical difficulties. Really need AI for this. So what we want to show today is that Tesla is much more than an electric car company, that we have deep AI activity in hardware, on the inference level, on the training level, and basically I think we're arguably the leaders in real-world AI as it applies to the real world. And those of you who have seen the full self-driving beta, I can appreciate the rate at which the Tesla neural net is learning to drive. And so this is a particular application of AI, but I think there are more applications down the road that will make sense, and we'll talk about that later in the presentation. But yeah, we basically want to encourage anyone who is interested in solving real-world AI problems at either the hardware or the software level to join Tesla, or consider joining Tesla. So let's see, we'll start off with Andre. If not, I can give you mine.
It doesn't sound like it? Okay, hello. Great. Okay, hi everyone. Welcome. My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under-the-hood components that go into making the car drive all by itself. So we're going to start off with the vision component here. Now, in the vision component, what we're trying to do is we're trying to design a neural network that processes the raw information, which in our case is the 8 cameras that are positioned around the vehicle. And they send us images, and we need to process that in real time into what we call the vector space. And this is a 3-dimensional representation of everything you need for driving. So this is the 3-dimensional positions of lines, edges, curbs, traffic signs, traffic lights, cars, their positions, orientations, depths, velocities, and so on. So here I'm showing a video of, actually, hold on. Apologies. So here I'm showing the video of the raw inputs that come into the stack, and then the neural network processes that into the vector space. And you are seeing parts of that vector space rendered in the instrument cluster on the car. Now, what I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. So the car can be thought of as an animal. It moves around, it senses the environment, and acts autonomously and intelligently. And we are building all of the components from scratch in-house. So we are building, of course, all of the mechanical components of the body, the nervous system, which is all of the electrical components, and for our purposes, the brain of the autopilot, and specifically for this section, the synthetic visual cortex. Now, the biological visual cortex actually has quite intricate structure and a number of areas that organize the information flow of this brain. And so in particular, in your visual cortices, the information hits the light, hits the retina, goes through the LGN all the way to the back of your visual cortex, goes through areas V1, V2, V4, the IT, the ventral and the dorsal streams, and the information is organized in a certain layout. And so when we are designing the visual cortex of the car, we also want to design the neural network architecture of how the information flows in the system. So the processing starts in the beginning when light hits our artificial retina, and we are going to process this information with neural networks. Now, I'm going to roughly organize this section chronologically. So starting off with some of the neural networks and what they looked like roughly 4 years ago when I joined the team, and how they have developed over time. So roughly 4 years ago, the car was mostly driving in a single lane, going forward on the highway, and so it had to keep lane and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. So this processing took the following shape. We take a 1280 by 960 input, and this is 12-bit integers streaming in at roughly 36 hertz. Now we're going to process that with a neural network. So we instantiate a feature extractor backbone. In this case, we use residual neural networks. So we have a stem and a number of residual blocks connected in series. Now the specific class of ResNets that we use are RegNets, because RegNets offer a very nice design space for neural networks because they allow you to very nicely trade off latency and accuracy. Now these RegNets give us as an output a number of features at different resolutions and different scales. So in particular, on the very bottom of this feature hierarchy, we have very high resolution information with very low channel counts. And all the way at the top, we have low resolution spatially, but high channel counts. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and have a lot of that context, have a lot of that scene context. We then like to process this with feature pyramid networks. In our case, we like to use BiFPNs, and they get to multiple scales to talk to each other effectively and share a lot of information. So for example, if you're a neuron all the way down in the network and you're looking at a small patch and you're not sure if this is a car or not, it definitely helps to know from the top layers that, hey, you are actually in the vanishing point of this highway. And so that helps you disambiguate that this is probably a car. After a BiFPN and a feature fusion across scales, we then go into task-specific heads. So for example, if you are doing object detection, we have a one-stage YOLO-like object detector here where we initialize a raster, and there's a binary bit per position telling you whether or not there's a car there. And then in addition to that, if there is, here's a bunch of other attributes you might be interested in. So the XY with height offset, or any of the other attributes, like what type of a car is this, and so on. So this is for the detection by itself. Now, very quickly we discovered that we don't just want to detect cars, we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly we converge in this kind of an architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, hydranets, and these are the heads of the hydra. Now, this architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks, so we can individually work on every one task in isolation. And for example, we can uprev any of the data sets or change some of the architecture of the head and so on, and you are not impacting any of the other tasks. And so we don't have to revalidate all the other tasks, which can be expensive. And number three, because there's this bottleneck here in features, what we do fairly often is that we actually cache these features to disk, and when we are doing these fine-tuning workflows, we only fine-tune from the cached features up and only fine-tune the heads. So most often in terms of our training workflows, we will do an end-to-end training run once in a while where we train everything jointly, then we cache the features at the multi-scale feature level, and then we fine-tune off of that for a while, and then end-to-end train once again, and so on. So here's the kinds of predictions that we were obtaining, I would say several years ago now, from one of these hydranets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images. So for example, here you can see predictions of the stop signs, the stop lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked, all of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the Hydra net. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is summoning the car. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we call the Occupancy Tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now there were two major problems, I would say, with this setup. Number one, we very quickly discovered that tuning the occupancy tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside a neural network and train that end to end. Number two, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible, and we are not going to be able to drive on this. So you see how the predictions are quite bad in vector space, and the reason for this fundamentally is because you need to have an extremely accurate depth per pixel in order to actually do this projection. And so you can imagine just how high of a bar it is to predict that depth so accurately in every single pixel of the image. And also if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image space concept in that case. So we very quickly the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now this is very easily said, much more difficult to actually achieve. But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them, and we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, so there are two problems with this. Problem number one, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number two, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling images and so on is not going to get you there. You need vector space labels. We're going to talk a lot more about problem number 2 later in the talk. For now, I want to focus on the neural network architectures, so I'm going to deep dive into problem number 1. So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions. So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images, and the evidence for whether or not this is a curb may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data-dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer to represent this space. And this transformer, it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values, and then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff, and that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation. So if you do all of the engineering correctly, this again is very easily said, difficult to do. You do all of the engineering correctly. There's one more problem actually before. I'm not sure what's up with the slides. So one more thing, you have to be careful with some of the details here when you are trying to get this to work. So in particular, all of our cars are slightly cockeyed in a slightly different way. And so if you're doing this transformation from image space to the output space, you really need to know what your camera calibration is. And you need to feed that in somehow into the neural net. And so you could definitely just like concatenate the camera calibrations of all of the images and somehow feed them in with an MLP. But actually we found that we can do much better by transforming all of the images into a synthetic virtual camera using a special rectification transform. So this is what that would look like. We insert a new layer right above the image, rectification layer. It's a function of camera calibration, and it translates all of the images into a virtual common camera. So if you were to average up a lot of repeater images, for example, which face to the back, without doing this, you would get a kind of a blur. But after doing the rectification transformation, you see that the back mirror gets really crisp. So once you do this, this improves the performance quite a bit. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. Okay, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space. But we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context, and we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there, even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know of the signs or the road markings that I saw 50 meters ago. So we try to develop, we try to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. So we have the multi-scale features as we had them from before, and what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. And then we're going to continue into the heads that do the decoding. Now, I'm going to go into both of these blocks one by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled. So here's the feature queue and the rough layout of it. We are basically concatenating these features over time and the kinematics of how the car has moved and the positional encodings, and that's being concatenated, encoded, and stored in a feature queue. And that's going to be consumed by a video module. Now there's a few details here again to get right. So in particular, with respect to the pop and push mechanisms, and when do you push, and how, and especially when do you push, basically. So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module. Now, for the video module, we looked at a number of possibilities of how to fuse this information temporally. So we looked at three-dimensional convolutions, transformers, axial transformers in an effort to try to make them more efficient, recurrent neural networks of a large number of flavors. But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces, we can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of. So here's an example of what that looks like. Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN. And these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road. Like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the Spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here, and basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent, and you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our Remove the Radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network, so we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. So here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through regnets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module like the Spatial RNN, and then continues into the branching structure of the HydroNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions sort of visualized both in a top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom. Or for example, our outputs are dense rasters, and it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very strict latency requirements, so this is not ideal. We actually are looking into all kinds of ways of predicting just the sparse structure of the road, maybe like point by point, or in some other fashion that doesn't require expensive post-processing. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run play and control on top of it.
Thank you, Andre. Hi, everyone. My name is Ashok. I lead the planning and controls, auto labeling and simulation teams. So, like Andre mentioned, the vision networks take dense video data and then compress it down into a 3D vector space. The role of the planner now is to consume this vector space and get the car to the destination while maximizing the safety, comfort, and the efficiency of the car. Even back in 2019, our planner was a pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city driving is much more complicated. Rarely there are structured lane lines. Vehicles do much more free-form driving. Then the car has to respond to all of curtains and crossing vehicles and pedestrians doing funny things. What is the key problem in planning? Number one, the action space is very non-convex. And number two, it is high dimensional. What I mean by non-convex is there can be multiple possible solutions that can be independently good, but getting a globally consistent solution is pretty tricky. So there can be pockets of local minima that the planning can get stuck into. And secondly, the high dimensionality comes because the car needs to plan for the next 10 to 15 seconds. It needs to produce the position, velocities, and acceleration over this entire window. This is a lot of parameters to produce at runtime. Discrete search methods are really great at solving non-convex problems because they are discrete, they don't get stuck in local minima, whereas continuous function optimization can easily get stuck in local minima and produce poor solutions that are not great. On the other hand, for high-dimensional problems, discrete search sucks because it is discrete, it does not use any graded information, so literally it has to go and export each point to know how good it is. Whereas continuous optimization uses gradient-based methods to very quickly go to a good solution. Our solution to this entire problem is to break it down hierarchically. First, use a code search method to crunch down the non-convexity and come up with a convex corridor, and then use continuous optimization techniques to make the final smooth trajectory. Let's see an example of how the search operates. Goes by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all physics-based models, these futures are very easy to simulate. And in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path. And you can see that when driving alongside other agents, it's important to not just plan for ourselves, but instead we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here, there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side. But the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown in green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they're actually going to go around these parked cars. So autopilot decides that, okay, I have space here, this person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car. So now we saw how the search and planning for other people set up a convex valley. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor, and we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up for, here on the right side, the green plot. Has a nice trapezoidal shape, and if you record a human trajectory, this is pretty much how it looked like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path. Together, these can do some really neat things like shown above. But driving looks a bit different in other places, like where I grew up from. It's very much more unstructured. Cars and pedestrians cutting each other, harsh braking, honking. It's a crazy world. We can try to scale up these methods, but it's going to be really difficult to efficiently solve this at runtime. What we instead want to do is use learning-based methods to efficiently solve them. And I want to show why this is true. So we're going to go from this complicated problem to a much simpler toy parking problem, but it still illustrates the core of the issue. Here, this is a parking lot. The ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. So this is a simple baseline. It's a A-star, it's a standard algorithm that uses a lattice space search. And the heuristic here is the distance, the Euclidean distance to the goal. So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima. And it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes for making this. Obviously, this is a terrible heuristic. We want to do better than this. So if you added a navigation route to it and has the car to follow the navigation route while being close to the goal, this is what happens. The navigation route helps immediately, but still, when it encounters cones or other obstacles, it basically does the same thing as before, backtracks and then searches a whole new path. And this poor search has no idea that these obstacles exist. It literally has to go there, check if it's in collision, and if it's in collision, back up. The navigation heuristic helped, but still this took 22,000 nodes. We can design more and more of these heuristics to help the search go faster and faster, but it's really tedious and hard to design a globally optimal heuristic. Even if you had a distance function from the cones that guided the search, this would only be effective for the single cone. But what we need is a global value function. So instead, what we want to use is neural networks to give this heuristic for us. The vision networks produces a vector space, and we have cars moving around in it. This basically looks like an Atari game, and it's a multiplayer version. So we can use techniques such as mu0, alpha0, etc., that was used to solve Go and other Atari games to solve the same problem. So we're working on neural networks that can produce state and action distributions that can then be plugged into Monte Carlo tree search with various cost functions. Some of the cost functions can be explicit cost functions like distance to collisions, comfort, traversal time, etc. But they can also be interventions from the actual manual driving events. We trained such a network for this simple parking problem. So here again, the same problem. Let's see how MCTS tree search does. So here you notice that the planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible options. It's not choosing any of them, just choosing the option that directly takes it towards the goal. The reason is that the neural network is able to absorb the global context of the scene and then produce a value function that effectively guides it towards the global minima as opposed to getting stuck in any local minima. So this only takes 288 nodes and is several orders of magnitude less than what was done in the A-star with the Euclidean distance heuristic. So this is what a final architecture is going to look like. The vision system is going to crush down the dense video data into a vector space. It's going to be consumed by both an explicit planner and a neural network planner. In addition to this, the network planner can also consume intermediate features of the network. Together, these produce a trajectory distribution, and it can be optimized end-to-end, both with explicit cost functions and human intervention and other imitation data. This then goes into explicit planning function that does whatever is easy for that and produces the final steering and acceleration commands for the car. With that, we need to now explain how we train these networks. And for training these networks, we need large data sets. I invite Andre to speak briefly about manual labeling.
Yeah, so the story of data sets is critical, of course. So far, we've talked only about neural networks, but neural networks only establish an upper bound on your performance. Many of these neural networks, they have hundreds of millions of parameters, and these hundreds of millions of parameters, they have to be set correctly. If you have a bad setting of parameters, it's not going to work. So neural networks are just an upper bound. You also need massive data sets to actually train the correct algorithms inside them. Now, in particular, I mentioned we want data sets directly in the vector space. And so really the question becomes, how can you accumulate, because our networks have hundreds of millions of parameters, how do you accumulate millions and millions of vector space examples that are clean and diverse to actually train these neural networks effectively? Now, so there's a story of data sets and how they've evolved on the side of all of the models and developments that we've achieved. Now, in particular, when I joined roughly 4 years ago, we were working with a third party to obtain a lot of our data sets. Now, unfortunately, we found very quickly that working with a third party to get data sets for something this critical was just not going to cut it. The latency of working with a third party was extremely high, and honestly, the quality was not amazing. And so in the spirit of full vertical integration at Tesla, we brought all of the labeling in-house. And so over time, we've grown more than 1,000-person data labeling org that is full of professional labelers who are working very closely with the engineers. So actually, they're here in the US and co-located with the engineers here in Bay Area as well. And so we work very closely with them. And we also build all of the infrastructure for them from scratch ourselves. So we have a team we are going to meet later today that develops and maintains all of this infrastructure for data labeling. And so here, for example, I'm showing some of the screenshots of some of the latency, throughput, and quality statistics that we maintain about all of the labeling workflows and the individual people involved and all the tasks and how the numbers of labels are growing over time. So we found this to be quite critical, and we're very proud of this. Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space. And so you can imagine that this is taking quite some time to annotate an image like this, and this is what it looked like, where we are sort of drawing polygons and polylines on top of these single individual images. As I mentioned, we need millions of vector space labels, so this is not going to cut it. So very quickly, we graduated to 3-dimensional or 4-dimensional labeling, where we are directly labeling in vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon, but it's a very small reconstruction of the ground plane on which the car drove, and a little bit of the point cloud here that was reconstructed. And what you're seeing here is that the labeler is changing the labels directly in vector space, and then we are reprojecting those changes into camera images. So we're labeling directly in vector space, and this gave us a massive increase in throughput for a lot of our labels, because you label once in 3D, and then you get to reproject. But even this, we realized, was actually not going to cut it. So because people and computers have different pros and cons. So people are extremely good at things like semantics, but computers are very good at geometry, reconstruction, triangulation, tracking. And so really for us, it's much more becoming a story of how do humans and computers collaborate to actually create these vector space data sets. And so we're gonna now talk about auto labeling, which is some of the infrastructure we've developed for labeling these clips at scale.
Hi again. So even though we have lots of human labelers, the amount of training data needed for training the network significantly outnumbers them. So we try to invest in a massive auto labeling pipeline. Here's an example of how we label a single clip. A clip is an entity that has dense sensor data, like videos, IMU data, GPS, odometry, etc. These can be 45 seconds to a minute long. These can be uploaded by our own engineering cars or from customer cars. We collect these clips and then send them to our servers, where we run a lot of neural networks offline to produce intermediate results, like segmentation masks, depth, point matching, etc. This then goes through a lot of robotics and AI algorithms to produce a final set of labels that can be used to train the networks. One of the first tasks we want to label is the road surface. Typically, we can use splines or meshes to represent the road surface, but those are, because of the topology restrictions, are not differentiable and not amenable to producing this. So what we do instead is in the style of neural radiance fields work from last year, which is quite popular. So we use an implicit representation to represent the road surface. Here, we are querying XY points on the ground and asking for the network to predict the height of the ground surface, along with various semantics such as curbs, lane boundaries, road surface, drivable space, etc. So given a single XY, we get a Z. Together, these make a 3D point. and they can be reprojected into all the camera views. So we make millions of such queries and get lots of points. These points are reprojected into all the camera views. We are showing on the top right here one such camera image with all these points reprojected. Now we can compare this point, reprojected point with the image space prediction of the segmentations. And jointly optimizing this over all the camera views, both across space and time, produces an excellent reconstruction. Here's an example of how that looks like. So here, this is an optimized road surface that reprojects into the 8 cameras that the car has and across all of time. And you can see how it's consistent across both space and time. So one more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say, in the car, the network needs to produce the velocity. It just has to use the historical information and guess what the velocity is. But here, we can look at both the history but also the future and basically cheat and get the correct answer of the kinematics, like velocity, acceleration, etc. One more advantage is that we can have like different tracks, but we can stitch them together even through occlusions. Because we know the future, we have future tracks, we can match them and then associate them. So here you can see the pedestrians on the other side of the road are persisted even through multiple occlusions by these cars. This is really important for the planner because the planner needs to know if it saw someone, it still needs to account for them even then they are occluded. So this is a massive advantage. Combining everything together, we can produce these amazing data sets that annotate all of the road texture, all of the static objects, and all of the moving objects even through occlusions, producing excellent kinematic labels. You can see how the cars turn smoothly, produce really smooth labels. All the pedestrians are consistently tracked. The parked cars have basically zero velocity, so we can also know that they are parked. So this is huge for us. This is one more example of the same thing. You can see how everything is consistent. We want to produce 1 million such labeled clips and train our video, multicam video networks with such large data set and really crush this problem. We want to get the same view that's consistent that we're seeing here in the car. We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably because obviously this truck just dumped a bunch of snow on us and it's really hard to see. But we should still remember that this car was in front of us. But our networks early on did not do this because of the lack of data in such conditions. So what we did, we asked the fleet to produce lots of similar clips, and the fleet responded, it did. So it produces, does it play? Yeah. It produces lots of video clips where shit's falling out of all other vehicles. And we sent this through our auto labeling pipeline that was able to label 10K clips within a week. This would have taken several months with humans labeling every single clip here. So we did this for 200 different conditions, and we were able to very quickly create large data sets, and that's how we were able to remove this. So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this. So finally, we wanted to actually get a Cybertruck into a data set for the Remove the Radar. Can you all guess where we got this clip from? I'll give you a moment. Someone said it. Yes, it's rendered. It's our simulation. It was hard for me to tell initially, and if I may say so myself, it looks pretty. It looks very pretty. So yeah, in addition to auto labeling, we also invest heavily in using simulation for labeling our data. So this is the same scene as seen before, but from a different camera angle. So a few things that I wanted to point out. For example, the ground surface. It's not plain asphalt. There are lots of cars and cracks and tar seams. There's some patchwork done on top of it. Vehicles move realistically. The truck is articulated, even goes over the curb and makes a wide turn. The other cars behave smartly. They avoid collisions, go around cars, and also smooth and accelerate smoothly, brake and accelerate smoothly. The car here with the logo on the top is autopilot. Actually, autopilot is driving that car, and it's making an unprotected left turn. And since this is simulation, it starts from the vector space. So it has perfect labels. Here we show a few of the labels that we produce. These are vehicle cuboids with kinematics, depth, surface normals, segmentation. But Andre can name a new task that he wants next week, and we can very quickly produce this because we already have the vector space, and we can write the code to produce these labels very, very quickly. So when does simulation help? It helps, number one, when the data is difficult to source. As large as our fleet is, it can still be hard to get some crazy scenes, like this couple and their dog running on the highway, while there are other high-speed cars around. This is a pretty rare scene, I'd say, but still can happen, and Autopilot still needs to handle it when it happens. When data is difficult to label, there are hundreds of pedestrians crossing the road. This could be a Manhattan, downtown, people crossing the road. It's going to take several hours for humans to label this clip. And even for automatic labeling algorithms, this is really hard to get the association right, and it can produce like bad velocities. But in simulation, this is trivial because you already have the objects. You just have to like spit out the cuboids and the velocities. And also, finally, when we introduce closed-loop behavior, where the cars needs to be in a determined situation, or the data depends on the actions, this is pretty much the only way to get it reliably. All this is great. What's needed to make this happen? Number one, accurate sensor simulation. Again, the point of the simulation is not to just produce pretty pictures. It needs to produce what the camera in the car would see and other sensors would see. So here, we are stepping through different exposure settings of the real camera on the left side and the simulation on the right side. We're able to pretty much match what the real cameras do. In order to do this, we had to model a lot of the properties of the camera in our sensor simulation, starting from sensor noise, motion blur, optical distortions, even headlight transmissions, even like diffraction patterns of the windshield, etc. We don't use this just for the Autopilot software. We also use it to make hardware decisions such as lens design, camera design, sensor placement, even headlight transmission properties. Second, we need to render the visuals in a realistic manner. You cannot have what in the game industry called jaggies. These are aliasing artifacts that are a dead giveaway that this is simulation. We don't want them. So we go through a lot of paints to produce nice spatiotemporal anti-aliasing. We also are working on neural rendering techniques to make this even more realistic. Yeah. In addition, we also use ray tracing to produce realistic lighting and global illumination. Okay, that's the last of the cop cars, I think. We obviously cannot have really just 4 or 5 cars because the network will easily overfit because it knows the sizes. So we need to have realistic assets, like the moose on the road here. We have thousands of assets in our library, and they can wear different shirts and actually can move realistically. So this is really cool. We also have a lot of different locations mapped and created to create these sim environments. We have actually 2,000 miles of road built. And this is almost the length of the roadway from the east coast to the west coast of the United States, which I think is pretty cool. In addition, we have built efficient tooling to build several miles more on a single day for a single artist. But this is just the tip of the iceberg. Actually, most of the data that we use to train is created procedurally using algorithms, as opposed to artists making these simulation scenarios. So these are all procedurally created roads with lots of parameters such as curvature, various varying trees, cones, poles, cars with different velocities, and the interaction produce an endless stream of data for the network. But a lot of this data can be boring because the network may not already get it correct. So what we do is we use also ML-based techniques to basically perturb the network to see where it's failing at and create more data around the failure points of the network. So this is in closed loop trying to make the network performance be better. We don't want to stop there. So actually, we want to recreate any failures that happens to the autopilot in simulation so that we can hold autopilot to the same bar from then on. So here, on the left side, you're seeing a real clip that was collected from a car. It then goes through our auto-labeling pipeline to produce a 3D reconstruction of the scene along with all the moving objects. With this, combined with the original visual information, we recreate the same scene synthetically and create a simulation scenario entirely out of it. So, and then when we replay autopilot on it, autopilot can do entirely new things, and we can form new worlds, new outcomes from the original failure. This is amazing because we really don't want autopilot to fail, and when it fails, we want to capture it and keep it to that bar. Not just that, we can actually take the same approach that we said earlier and take it one step further. We can use neural rendering techniques to make it look even more realistic. So we take the original video clip, recreate a synthetic simulation from it, and then apply neural rendering techniques on top of it, and it produces this, which looks amazing in my opinion, because this one is very realistic and looks almost like it was captured by the actual cameras. This is a result from last night, because it was cool and we wanted to present it. But yeah, I'm very excited for what Sim can achieve. But this is not all bullshit, because networks trained in the car already use simulation data. We used 300 million images with almost 500 million labels. And we want to crush down all the tasks that are going to come up for the next several months. With that, I invite Milan to explain how we scale these operations and really build a label factory and spit out millions of labels.
All right, thanks, Ashok. Hey, everyone, I'm Milan. I'm responsible for the integration of our neural networks in the car and for most of our neural network training and evaluation infrastructure. And so tonight, I'd just like to start by giving you some perspective into the amount of compute that's needed to power this type of data generation factory. And so in the specific context of the push we went through as a team here a few months ago to get rid of the dependency on the radar sensor for autopilot, we generated over 10 billion labels across 2.5 million clips. And so to do that, we had to scale our huge offline neural networks and our simulation engine across thousands of GPUs and just a little bit shy of 20,000 CPU cores. On top of that, we also included over 2,000 actual autopilot full self-driving computers in the loop with our simulation engine. And that's our smallest compute cluster. So I'd like to give you some idea of what it takes to take our neural networks and move them in the car. And so the two main constraints that we're working under here are mostly latency and frame rate, which are very important for safety, but also to get proper estimates of acceleration and velocity of our surroundings. And so the meat of the problem really is around the AI compiler that we write and extend here within the group that essentially maps the compute operations for my PyTorch model to a set of dedicated and accelerated pieces of hardware. And we do that while figuring out a schedule that's optimized for throughput while working under severe SRAM constraints. And so, by the way, we're not doing that just on one engine, but across two engines on the autopilot computer. And the way we use those engines here at Tesla is such that at any given time, only one of them will actually output control commands to the vehicle, while the other one is used as an extension of compute. But those roles are interchangeable, both at the hardware and software level. So how do we iterate quickly together as a group through these AI development cycles? Well, first, we have been scaling our capacity to evaluate our software and neural network dramatically over the past few years. And today, we're running over 1 million evaluations per week on any code change that the team is producing. And those evaluations run on over 3,000 actual full self-driving computers that are hooked up together in a dedicated cluster. And so on top of this, we've been developing really cool debugging tools. And so here is a video of one of our tools, which is helping developers iterate through the development of neural networks and comparing live the outputs from different revisions of a same neural network model as we're iterating live through video clips. And so last but not least, we've been scaling our neural network training compute dramatically over the past few years. And today we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world. But that's not enough, and so I'd like to invite Ganesh to talk about the next steps.
Thank you, Milan. My name is Ganesh, and I lead Project Dojo. It's an honor to present this project on behalf of the multidisciplinary Tesla team that is working on this project. As you saw from Milan, there's an insatiable demand for speed as well as capacity for neural network training. And Elon prefetched this, and a few years back, he asked us to design a super fast training computer, and that's how we started Project Dojo. Our goal is to achieve best AI training performance and support all these larger, more complex models that Andre's team is dreaming of, and be power efficient and cost effective at the same time. So we thought about how to build this, and we came up with a distributed compute architecture. After all the training computers out there are distributed computers in one form or the other. They have compute elements in the box out here connected with some kind of network. In this case, it's a two-dimensional network, but it could be any different network. CPU, GPU, accelerators, all of them have compute, little memory, and network. But one thing which is common trend amongst this is it's easy to scale the compute. It's very difficult to scale up bandwidth and extremely difficult to reduce latencies. And you'll see how our design point catered to that, how our philosophy addressed these aspects of traditional limits. For Dojo, we envisioned a large compute plane filled with very robust compute elements backed with large pool of memory and interconnected with very high bandwidth and low latency fabric and in a 2D mesh format. And on to this, for extreme scale, big neural networks will be partitioned and mapped to extract different parallelism, model, graph, data parallelism. And then a neural compiler of ours will exploit spatial and temporal locality such that it can reduce communication footprint to local zones and reduce global communication. And if we do that, our bandwidth utilization can keep scaling with the plane of compute that we desire out here. We wanted to attack this all the way, top to bottom of the stack, and remove any bottlenecks at any of these levels. And let's start this journey in an inside-out fashion, starting with the chip. As I described, chips have compute elements. Our smallest entity of scale is called a training node. And the choice of this node is very important to ensure seamless scaling. If you go too small, it will run fast, but the overheads of synchronization and software will dominate. If you pick it too big, it will have complexities in implementation in the real hardware and ultimately run into memory bottleneck issues. Because we wanted to address latency and bandwidth as our primary optimization point. Let's see how we went about doing this. What we did was we picked the farthest distance a signal could traverse in a very high clock cycle, in this case, 2 gigahertz plus. And we drew a box around it. This is the smallest latency that a signal can traverse, one cycle at a very high frequency. And then we filled up the box with wires to the brink. This is the highest bandwidth you can feed the box with. And then we added machine learning compute underneath, and then a large pool of SRAM. And last but not the least, a programmable core to control. And this gave us our high performance training node. What this is a 64-bit superscalar CPU optimized around matrix multiply units and vector SIMD. It supports floating point 32, bfloat 16, and a new format, CFP8, configurable FP8. And it is backed by 1.25 megabyte of fast ECC protected SRAM and the low latency, high bandwidth fabric that we designed. This might be our smallest entity of scale, but it packs a big punch. More than 1 teraflop of compute in our smallest entity of scale. So let's look at the architecture of this. The computer architects out here may recognize this. This is a pretty capable architecture as soon as you see this. It is a superscalar in-order CPU with 4 wide vector and 4 wide scalar and 2 wide vector pipes. We call it in order, although the vector and the scalar pipes can go out of order, but for the purists out there, we still call it in order. And it also has 4-way multi-threading. This increases utilization because we could do compute and data transfers simultaneously. And our custom ISA, which is the instruction set architecture, is fully optimized for machine learning workloads. It has features like transpose, gather, link traversals, broadcast, just to name a few. And even in the physical realm, we made it extremely modular, such that we could start abutting these training nodes in any direction and start forming the compute plane that we envisioned. When we click together 354 of these training nodes, we get our compute array. It's capable of delivering 362 teraflops of machine learning compute. And of course, the high bandwidth fabric that interconnects these. And around this compute array, we surrounded it with high-speed, low-power services, 576 of them, to enable us to have extreme I/O bandwidth coming out of this chip. Just to give you a comparison point, this is more than 2 times the bandwidth coming out of the state-of-the-art networking switch chips which are out there today. And network switch chips are supposed to be the gold standards for I/O bandwidth. If we put all of it together, we get training optimized chip, our D1 chip. This chip is manufactured in 7 nanometer technology. It packs 50 billion transistors in a miserly 645 millimeter square. One thing you'll notice, 100% of the area out here is going towards machine learning training and bandwidth. There is no dark silicon, there is no legacy support. This is a pure machine learning machine. And this is the D1 chip in a flip chip BGA package. This was entirely designed by Tesla team internally, all the way from the architecture to GDS out and package. This chip is like a GPU level compute with a CPU level flexibility and twice the network chip level I/O bandwidth. If I were to plot the I/O bandwidth on the vertical scale versus teraflops of compute that is available in the state-of-the-art machine learning chips out there, including some of the startups, you can easily see why our design point excels beyond par. Now that we had this fundamental physical building block, how to design the system around it? Let's see. Since D1 chips can seamlessly connect without any glue to each other, we just started putting them together. We just put 500,000 training nodes together to form our compute plane. This is 1,500 D1 chips seamlessly connected to each other. And then we add Dojo interface processors on each end. This is the host bridge to typical hosts in the data centers. It's connected with PCI Gen 4 on one side with a high bandwidth fabric to our compute plane. The interface processors provide not only the host bridge, but high bandwidth DRAM shared memory for the compute plane. In addition, the interface processors can also allow us to have a higher radix network connection. In order to achieve this compute plane, we had to come up with a new way of integrating these chips together. And this is what we call as a training tile. This is the unit of scale for our system. This is a groundbreaking integration of 25 known good D1 dies onto a fan-out wafer process, tightly integrated such that it preserves the bandwidth between them. The maximum bandwidth is preserved there. And in addition, we generated a connector, a high bandwidth, high density connector that preserves the bandwidth coming out of this training tile. And this tile gives us 9 petaflops of compute with a massive I/O bandwidth coming out of it. This perhaps is the biggest organic MCM in the chip industry, multi-chip module. It was not easy to design this. There were no tools that existed. All the tools were croaking. Even our compute cluster couldn't handle it. Our engineers came up with different ways of solving this. They created new methods to make this a reality. Now that we had our compute plane tile with high bandwidth IOs, we had to feed it with power. And here, we came up with a new way of feeding power vertically. We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB-level technology of reflow onto this fan-out wafer technology. This is a lot of integration already out here, but we didn't stop here. We integrated the entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated, interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering. Our compute plane is completely orthogonal to power supply and cooling. That makes high bandwidth compute planes possible. What it is a 9 petaflop training tile. This becomes our unit of scale for our system. And this is real. I can't believe I'm holding 9 petaflops out here. And in fact, last week, we got our first functional training tile. And on a limited cooling benchtop setup, we got some networks running. And I was told Andre doesn't believe that we could run networks till we could run one of his creations. Andre, this is MinGPT-2 running on Dojo. Do you believe it? Next up, how to form a compute cluster out of it. By now, you must have realized our modularity story is pretty strong. We just put together some tiles. We just tiled together tiles. A 2x3 tile in a tray makes our training matrix, and 2 trays in a cabinet give 100 petaflops of compute. Did we stop here? No. We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through, preserving the bandwidth. There's no bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this, we have an exapod. This is 1 exaflop of compute in 10 cabinets. It's more than 1 million training nodes that you saw. We paid meticulous attention to that training node, and there are 1 million nodes out here with uniform bandwidth. Not just the hardware, the software aspects are so important to ensure scaling. And not every job requires a huge cluster, so we planned for it right from the get-go. Our compute plane can be subdivided, can be partitioned into units called Dojo Processing Unit. A DPU consists of one or more D1 chips. It also has our interface processor and one or more hosts. And this can be scaled up or down as per the needs of any algorithm, any network running on it. What does the user have to do? They have to change their scripts minimally. And this is because of our strong compiler suite. It takes care of fine-grained parallelism and mapping the problems of mapping the neural networks very efficiently onto our compute plane. Our compiler uses multiple techniques to extract parallelism. It can transform the networks to achieve not only fine-grained parallelism using data model graph parallelism techniques, it also can do optimizations to reduce memory footprints. One thing, because of our high bandwidth nature of the fabric is enabled out here, is model parallelism could not have been extended to the same level as what we can. It was limited to chip boundaries. Now we can, because of our high bandwidth, we can extend it to training tiles and beyond. Thus, large networks can be efficiently mapped here at low batch sizes and extract utilization and new levels of performance. In addition, our compiler is capable of handling high-level dynamic control flows like loops, if then else, etc. And our compiler engine is just part of our entire software suite. The stack consists of an extension to PyTorch that ensures the same user-level interfaces that ML scientists are used to. And our compiler generates code on the fly such that it could be reused for subsequent execution. It has a LLVM backend that generates the binary for the hardware. And this ensures we can create optimized code for the hardware without relying on even single line of handwritten kernel. Our driver stack takes care of the multi-host, multi-partitioning that you saw a few slides back. And then we also have profilers and debuggers in our software stack. So with all this, we integrated in a vertical fashion. We broke the traditional barriers to scaling. And that's how we got modularity up and down the stack to add to new levels of performance. To sum it all, this is what it will be. It will be a fastest AI training computer, 4x the performance at the same cost, 1.3x better performance per watt, that is energy saving, and 5x smaller footprint. This will be Dojo computer. And we are not done. We are assembling our first cabinets pretty soon, and we have a whole next generation plan already. We are thinking about 10x more with different aspects that we can do, all the way from silicon to the system again. We will have this journey again. We're recruiting heavily for all of these areas. Thank you very much. And next up, Elon will update us on what's beyond our vehicle fleet for AI.
unlike Dojo, obviously that was not real. So Dojo is real. The Tesla bot will be real. But basically, if you think about what we're doing right now with the cars, Tesla is arguably the world's biggest robotics company because our cars are, like I said, semi-sentient robots on wheels. And with the full self-driving computer, essentially the inference engine on the car, which will keep evolving, obviously, and Dojo, and all the neural nets recognizing the world, understanding how to navigate through the world, it kind of makes sense to put that onto a humanoid form. And we're also quite good at sensors and batteries and actuators. So we think we'll probably have a prototype sometime next year that basically looks like this. And it's intended to be friendly, of course, and navigate through a world built for humans and eliminate dangerous, repetitive, and boring tasks. We're setting it such that it is, at a mechanical level, at a physical level, you can run away from it. And most likely overpower it. So hopefully that doesn't ever happen, but you never know. So it'll be a light, yeah, anyway, 5 miles an hour. You can run faster than that, it'll be fine. So yeah, it's around 5'8". Has sort of a screen where the head is for useful information, but it's otherwise basically got the autopilot system in it. So it's got cameras, got 8 cameras, and yeah. Full self-driving computer, and making use of all of the same tools that we use in the car. So, I mean, things I think that are really hard about having a useful humanoid robot is, can it navigate through the world without being explicitly trained? I mean, without explicit, like, line-by-line instructions. Can you talk to it and say, please pick up that bolt and attach it to the car with that wrench, and it should be able to do that. It should be able to, please go to the store and get me the following groceries, that kind of thing. So, yeah, I think we can do that. And yeah, this I think will be quite profound, because if you say it like, what is the economy? It is, at the foundation, it is labor. So what happens when there is, no shortage of labor? This is why I think long term that there will need to be universal basic income. Yeah. But not right now, because this robot doesn't work. So we just need a minute. So yeah, but I think essentially in the future, physical work will be a choice. If you want to do it, you can, but you won't need to do it. And yeah, I think it obviously has profound implications for the economy, because given that the economy at its foundational level is labor, I mean, capital equipment is just distilled labor, then is there any actual limit to the economy? Maybe not. So, yeah. Join our team and help build this. All right, so I think we'll have everyone come back on the stage, and you guys can ask questions if you'd like. Yeah.
Okay, I'm quietly starting to talk here so that you guys can adjust your volumes. oh wait, hold on.
Maybe try to get the camera angle from there, but not from the side. Thanks. All right, cool. So we'll probably turn the lights back on, and yeah, great. So we're happy to answer any questions you have about anything on the software, hardware side, where things are going, and yeah, fire away. Because the lights are like interrogation lights, we actually cannot see. There we go. Great.
Oh, yeah.
All right, cool.
I can just, okay, there we go. First off, I mean, thanks to all the presenters. That was just super cool to see everything. I'm just curious at a high level, and this is kind of a question for really anyone who wants to take it. To what extent are you interested in publishing or open sourcing anything that you do for the future?
Well, I mean, it is fundamentally extremely expensive to create the system, so somehow that has to be paid for. I'm not sure how to pay for it if it's fully open sourced. Yeah, unless people want to work for free. But I should say that this is, if other car companies want to license it and use it in their cars, that would be cool. This is not intended to be just limited to Tesla cars.
Is for the Dojo supercomputer. So did you solve the compiler problem of scaling to these many nodes, or if it is solved, is it only applicable to Dojo? Because I'm doing research in deep learning accelerators, and getting the correct scalability or the distribution, even in one chip, is extremely difficult from the research project's perspective. So I was just curious.
Excuse me, mic for Bill. You want to?
Have we solved the problem? Not yet. Are we confident we will solve the problem? Yes. We have demonstrated networks on prototype hardware now. We have models, performance models showing the scaling. The difficulty is, as you said, how do we keep the localities? If we can do enough model parallel, enough data parallel to keep most of the things local, we just keep scaling. We have to fit the parameters in our working set in our SRAM that we have, and we flow through the pipe. There's plenty of opportunities. Sorry, as we get further scale for further processor nodes, have more local memory trade-offs with bandwidth, we can do more things. But as we see it now, the applications that Tesla has, we see a clear path.
And our modularity story means we can have different ratios, different aspects created out of it. I mean, this is something that we chose for our applications internally.
Sure.
I was just saying that the locality portion of it, given that training is such a soft scaling application, even though you have all this compute and have a high bandwidth interconnect, it could not give you that performance because you're doing computations on limited memory at different locations. So I was that's very curious to me when you said it's solved, because I just jumped onto the opportunity and would love to know more, given that how much you can open source.
Right in there.
Yeah.
Yeah, I guess the proof's in the pudding. So we should have Dojo operational next year, and I think we'll obviously use it for training, video training. I mean, fundamentally, this is about like the primary application initially is we've got vast amounts of video, and how do we train vast amounts of video as efficiently as possible, and also shorten the amount of time. Like if you're trying to train to a task, like just in general, innovation is how many iterations and what is the average progress between each iteration. And so if if you can reduce the time between iterations, the rate of improvement is much better. So, if it takes like sometimes a couple days for a model to train versus a couple hours, that's a big deal. But the acid test here, and what I've told the Dojo team is like it's successful if the software team wants to turn off the GPU cluster. But if they want to keep the GPU cluster on, it's not successful. So.
Hi, Bert over here. Love the presentation. Thank you for getting us out here. Love everything, especially the simulation part of the presentation. I was wondering, it looked very realistic. Are there any plans to maybe expand simulation to other parts of the company in any way?
Hi, I'm Ian Glow. I manage the autopilot simulation team. So as we go down the path to full self-driving, we're going to have to simulate more and more of the vehicle. Currently, we're simulating vehicle dynamics, but we're going to need BMS, we're going to need the MCU, we're going to need every single part of the vehicle integrated. And that actually makes the autopilot simulator really useful for places outside of autopilot. So we want to expand eventually to being a universal simulation platform. But I think before that, we're going to be spinning up a lot of Optimus support. And then a little bit further down the line, we have some rough ideas on potentially how to get the simulation infrastructure and some of the cool things we've built into the hands of people outside of the company.
Optimus is the code name for the Tesla bot.
Oops.
Optimus subprime.
Yeah. Hi, this is Ali Jahanian. Thank you for the great presentation and putting all of these cool things together. Yeah, for a while I have been thinking that the car is already a robot. So why not a humanoid robot? And I'm so happy that today you mentioned that you are going to build such a thing. Especially, I think that this can give opportunity for ways of putting multi-modality together. For instance, we know that in the example that you showed that there was a dog and with some passengers or running together. The language and symbolic processing can really help for visualizing that. So I was wondering if I could hear a little more about this type of putting modalities together, including language and vision. Because I have been working with, for instance, mini GPT that Andre put out there. And yeah, I didn't hear much about other modalities that's going into the car, or at least in the simulation. Is there any comment that you could tell us?
Well, driving is fundamentally basically almost entirely vision neural nets. Basically, it's running on a biological vision neural net, and what we're doing here is a silicon camera neural net. So there is some amount of audio. You want to hear if there's like emergency vehicles, or I guess converse with the people in the car. If somebody's yelling something at the car, the car needs to understand what that is. So all the things that are necessary for it to be fully autonomous. Yeah. Thank you.
Hi, thank you for all the great work that you've shown. My question is for the team, because the data that was shown seems to be predominantly from the United States that the FSD computer is being trained on. But as it gets rolled out to different countries, which have their own road systems and challenges that come with it, how do you think that it's going to scale? Like I'm assuming the ground up is not a very viable solution. So how does that transfer to different countries?
Well, we actually do train on using data from probably like 50 different countries, but we have to pick. As we're trying to advance full self-driving, we need to pick one country, and since we're located here, we pick the US. And then we get a lot of questions like, why not even Canada? I'm like, well, because the roads are a little different in Canada, different enough. And so when trying to solve a hard problem, you want to say like, okay, what's the, let's not add additional complexity right now. Let's just solve it for the US, and then we'll extrapolate to the rest of the world. But we do use video from all around the world.
Yeah, I think a lot of what we are building is very country agnostic. Fundamentally, all the computer vision components and so on don't care too much about country-specific sort of features. Different countries have roads, and they have curbs, and they have cars, and everything we're building is fairly general for that.
Yeah, and there's the prime directive is don't crash.
Right, and that's true for every country.
Yes, this is the prime directive. I mean, even right now, the car is pretty good at not crashing. And so just basically, whatever it is, don't hit it. Even if it's a UFO that crash landed on the highway, and still don't hit it. You should not need to recognize it in order to not hit it. So that's very important.
And I want to ask that when you do the photometric process, multi-view geometry, how much of an error do you see? Is it like 1 millimeter, 1 centimeter? So I'm just, if it's not confidential.
Sorry, the question, what is the
what's the difference between the synthetic? Sure. What is the difference between the synthetically created geometry to the actual geometry?
Yeah, it's usually within a couple centimeters, 3 or 4 centimeters. That's the standard deviation.
With different kind of modalities to bring down that error.
We primarily try to find scalable ways to label. In some occasions, we use other sensors to help benchmark, but we primarily try to use cameras for this system.
Okay, thanks.
Yeah, I mean, I think we want to aim for the car to be positioned accurately to the sort of centimeter level, something on that order.
Obviously, it will depend on distance. Like close by things can be much more accurate than farther away things, and they would matter less because the car doesn't have to make decisions much farther away. And as it comes close, it will become more and more accurate.
Exactly. A lot of questions.
Thanks, everybody. My question has to do with sort of AI and manufacturing. It's been a while since we've heard about the alien dreadnought concept. Is the humanoid that's behind you guys, is that kind of brought out of the production hell timeline and saying that humans are underrated in that process?
Well, sometimes like something that I say is taken to too much of an extreme. There are parts of the Tesla system that are almost completely automated. And then there are some parts that are almost completely manual. If you were to walk through the whole production system, you would see a very wide range from, like I said, fully automatic to almost completely manual. But the vast majority, most of it is already automated. And then with some of the design architecture changes, like going to large aluminum high-pressure die-cast components, we can take the entire rear third of the car and cast it as a single piece. And now we're going to do the front third of the car as a single piece. So the body line drops by like 60 to 70% in size. But yeah, the robot is not prompted by specifically by manufacturing needs. It's just that we're just obviously making the pieces that are needed for a useful humanoid robot. So I guess we probably should make it. And if we don't, someone else will. And so I guess we should make it and make sure it's safe. I should say, like, also manufacturing, volume manufacturing is extremely difficult and underrated, and we've gotten pretty good at that. So it's also important for the humanoid robot. Like, how do you make the humanoid robot not be super expensive? And
Hi. Thank you for the presentation. And my question will be about scaling of Dojo. And in particular, how do you scale the compute nodes in terms of thermals and power delivery? Because there is only so much heat that you can dispense and only so much power that you can bring to like cluster rack. And how do you plan to scale it? And how do you plan to scale it in multiple data centers?
Sure. You want to take it? Oh, there.
Yeah, hi. I'm Bill. I'm one of the Dojo engineers. So from a thermal standpoint and power standpoint, we've designed it very modular. So what you saw in the compute tile, that will cool the entire tile. So once we hook it up to, it is liquid cooled on both the top and the bottom side. It doesn't need anything else. And so when we talk about clicking these together, once we click it to power and once we click it to cooling, it will be fully powered and fully cooled. And all of that is less than a cubic foot.
Yeah, so Tesla has a lot of expertise in power electronics and in cooling. So we took the power electronics expertise from the vehicle powertrain and the sort of the advanced cooling that we developed for the power electronics and for the vehicle and applied that to the supercomputer. Because as you point out, getting heat out is extremely important. It's just really heat limited. So, yeah, so it's funny that at the compute level, it's operating at less than a volt, which is a very low voltage. There's a lot of amps, so therefore a lot of heat. I squared R is really bites you on the ass.
Hi, my question's also similarly a question of scaling. So it seems like a natural consequence of using, significantly faster training hardware is that you'd be either training models over a lot more data, or you'd be training a lot more complex models, which would be potentially significantly more expensive to run at inference time on the cars. I guess I was wondering, if there was a plan to, also apply Dojo as something that you'd be using, on the self-driving cars, and if so, do you foresee additional challenges there?
So as you could see, Andre's models are not just for cars. There are auto labeling models, there are other models that are beyond car application, but they feed into the car stack. So Dojo will be used for all of those too, not just the car inference part of the training.
Yeah, I mean, the Dojo's first application will be consuming video data for training that would then be run in the inference engine on the car. But and that I think is an important test to see if it actually is good but is it actually better than GPU cluster or not? But then beyond that, it's basically a generalized neural net training computer. But it's very much optimized to be a neural net. So CPUs and GPUs, they're not made to be. They're not designed specifically for training neural nets. We've been able to make GPUs especially very efficient for training neural nets, but that was never their design intent. So it's basically GPUs are still essentially running at neural net training in emulation mode. So with Dojo, we're saying okay, let's just ASIC the whole thing. Let's just have this thing it's built for one purpose, and that is neural net training. And just generally, any system that is designed for a specific purpose will be better than one that is designed for a general purpose.
Hey, I have a question here. Hi. So you described two separate systems. One was for vision, other was for planner and control. Does Dojo allow you to train networks that cross that boundary? And second thing is, if you were able to train such networks, would you have the onboard compute capability in the FSD system to be able to run that under your tight latency constraints? Thanks.
Yeah, I think we should be able to train random networks on Dojo or any GPUs. It's really invariant to the platform. And I think, if anything, once we make this entire thing end-to-end, it will be more efficient than decoding a lot of these intermediate states. So we should be able to run faster if we make the entire thing end-to-end neural networks. We can avoid a lot of decoding of these intermediate states and only decode only essential things required for driving the car.
Yeah, certainly end-to-endness is the guiding principle behind a lot of the network developments. And over time in the stack, neural networks have taken on more and more functionality. And so we want everything to be trained end-to-end because we see that that works best. But we are building it incrementally. So right now, the interface, there is vector space, and we are consuming it in the planner, but nothing really fundamentally prevents you from actually taking features and eventually fine-tuning end-to-end. So I think that's definitely where this is headed.
Yeah. And the discovery really is like, what are the right architectures? Discovery really is like, what are the right architectures that we need to place in network blocks to make it amenable to that task. So like Andre described, we can place spatial RNNs to help with the perception problem. And now it's just neural network. So similarly for planning, we need to bake in search and optimization into the network architecture. And once we do that, you should be able to do planning very quickly, similar to C++ algorithms.
Okay. I think I had a question very similar to what he was asking about. It seems like a lot of neural nets are around computer vision. And kind of traditional planning, you had model predictive control and solving convex optimization problems very quickly. And I'd wonder if there's a compute architecture that's more suited for convex optimization or the model predictive control solutions very quickly.
Yeah, 100%. We want to bake in, like I said earlier, we want to bake in these architectures that do, say, model predictive control, but it just like replace some of the blocks with neural networks. Or if we know the physics of it, we can also use physics-based models, part of the neural networks forward pass itself. So we are going to go towards a hybrid system where we will have neural network blocks placed together with physics-based blocks and more neural networks later. So it will be a hybrid stack, and what we know to do well, we place it explicitly, and what the networks are great at, we'll use the networks to optimize this. So build an end-to-end stack with this architecture baked in.
I do think that so as long as you've got like surround video neural nets for understanding what's going on and can convert the surround video into vector space, then you basically have a video game. And if it's like if you're in Grand Theft Auto or whatever, you can make the cars drive around and pedestrians walk around without crashing. So you can do. You don't have to have a neural net for control and planning, but it's probably ultimately better. But I think you can probably get to. In fact, I'm sure you can get to much safer than human with control and planning, primarily in C++ with perception, vision in neural nets.
Hi. My question is, we've seen other companies, for example, use reinforcement learning and machine learning to optimize power consumption in data centers and all kinds of other internal processes. My question is Tesla using machine learning within its manufacturing design or other engineering processes?
I discourage use of machine learning because it's really difficult. Unless you have to use machine learning, don't do it. It's usually a red flag when somebody says, we want to use machine learning to solve this task. I'm like, that sounds like bullshit. 99.9% of the time, you do not need it. Yeah, so it's kind of like you reach for machine learning when you need to. No, but I've not found it to be a convenient, easy thing to do. It's a super hard thing to do. Now, that may change if you've got a humanoid robot that can, understand normal instructions. Yeah, generally minimize use of machine learning in the factory.
Hi. Based on your videos from the simulator, it looked like a combination of graphical and neural approaches. I'm curious what the set of underlying techniques that are used for your simulator and specifically for neural rendering, if you can share.
Yeah, so we're doing At the bottom of the stack, it's just traditional game techniques, just rasterization, real time, very similar to what you'd see in like GTA. On top of that, we're doing real time ray tracing, and then those results were really hot off the press. We had that little asterisk at the bottom that was from last night. We're going into the neural rendering space. We're trying out a bunch of different things. We want to get to the point where the neural rendering is the cherry on the top that pushes it to the point where the models will never be able to overfit on our simulator. Currently, we're doing things similar to photorealism enhancement. There's a recent paper enhancing photorealism enhancement, but we can do a lot more than what they could do in that paper because we have way more labeled data, way more compute, and also we have a lot more control over our environments. And we also have a lot of people who can help us make this run at real time. But we're going to try whatever we can do to get to the point where we can train everything just with the simulator if we had to, but we will never have to because we have so much real world data that no one else has. It's just to fill in the little gaps in the real world.
Yeah, the simulator is very helpful when there's these rare cases like collision avoidance right before an accident. And then, ironically, the better our cars become at avoiding accidents, the fewer accidents there are, so then our training set is small, so then we have to make them crash in the simulation. So it's like, okay, minimize potential injury to pedestrians and people in the car. You have 5 meters, you're traveling at 20 meters per second. What actions would minimize probability of injury? We can run that in sim. So, cars driving down the wrong side of the highway, that kind of thing. Happens occasionally, but not that often.
For your humanoid context, I'm wondering if you've decided on what use cases you're going to start with and what the grand challenges are in that context to make this viable.
Well, I think for the Tesla bot, Optimus, it's basically going to start with just dealing with work that is boring, repetitive, and dangerous. Basically, what is the work that people would least like to do?
Hi, so quick question about your simulations. Obviously, they're not perfect right now, so are you using any sort of domain adaptation techniques to basically bridge the gap between your simulated data and your actual real-world data? Because I imagine it's kind of dangerous to just deploy models which are solely trained on simulated data, so maybe some sort of explicit domain adaptation or something. Is that going on anywhere in your pipeline?
So currently, we're producing the videos straight out of the simulator, the full clips with kinematics and everything, and then we're just immediately training on them, but it's not the entire data set. It's just a small targeted segment, and we only are evaluating based on real world video. We're paying a lot of attention to make sure we don't overfit, and if we have to start doing fancier things, we will, but currently we're not having an issue with it overfitting on the simulator. We will as we scale up the data, and that's what we're hoping to use neural rendering to bridge that gap, to push that even further out. We've already done things where we're using the same network as in the car, but retrain it to detect sim versus real to drive our art decisions. And that's actually helped prevent some of these things as well.
Yeah, just to emphasize that overwhelmingly, the data set is the real video from the cars on the actual roads. Nothing's weirder or has more corner cases than reality. It gets really strange out there. But then if we find, say, a few examples of something very odd, and there's some very odd pictures we've seen, then in order to train it effectively, we want to create simulations, say 1,000 simulations that are variants of that quirky thing that we saw, to fill in some important gaps and make the system better. And really, all of this is about, over time, just reducing the probability of a crash or an injury, and just go the march of nines. Like, how do you get to 99.9999999% safe? And yeah, each 9 is an order of magnitude difficulty increase.
Hey all, thanks so much for the presentation. I was curious about the Tesla bot. Specifically, I'm wondering if there are any specific applications that you think the humanoid form factor lends itself to. And then secondary, because of its human form factor, is emotion or companionship at all thought about on the product roadmap at all?
Well, we certainly hope this does not feature in a dystopian sci-fi movie. But you know, like, really, at this point, we're saying like maybe this robot can we're trying to be as literal as possible. Can it do boring, dangerous, repetitive jobs that people don't want to do? And you know, once we can have it do that, then maybe we can do other things too. But that's the thing that would be really great to have. So it could be your buddy too. I mean, you can buy one and have it be your friend and whatever. I'm sure that people will think of some very creative uses.
So firstly, thanks for the really incredible presentation. My question's on the AI side. So one thing we've been seeing is that with some of these language modeling AIs, we've seen that scaling has just had incredible impacts in their capabilities and what they're able to do. So I was wondering whether you're seeing similar kinds of effects of scaling in your neural networks and your applications.
Absolutely. A bigger network, typically we see it performs better, provided you have the data to also train it with. And this is also what we see for ourselves. Definitely in the car, we have some latency consideration to be mindful of. And so there we have to get creative to actually deploy much, much larger networks. But as we mentioned, we don't only train neural networks for what goes in the car. We have these auto-labeling pipelines that can utilize models of arbitrary size. So in fact, we've trained a number of models that are not deployable, that are significantly larger and work much better because we want 100%, like we want much higher accuracy for the auto-labeling instruction, and then you distill that into neural networks that you deploy to the car. But we basically have a lot of neural networks and a lot of tasks that are never intended to go into the car.
Yeah, and also as time goes on, there you get new frames of information. So you really want to make sure your computer is distributed across all the information as opposed to just taking a single frame and hogging on it for, say, 200 milliseconds. You actually have newer frames coming in, so you want to like use all of the information and not just use that one frame.
I think one of the things we're seeing is that the car's predictive ability is eerily good. It's really getting better than human in terms of predicting, like you said, like predict what this road will look like when it's out of sight, like it's around the bend, and it predicts the road with very high accuracy. You know, predict pedestrians or cyclists where behind, you know, where it just sees a little corner of the bicycle and a little bit through the windows of the bus. And its ability to predict things is going to be much better than humans, like really way beyond.
Right. Yeah, we see this often where we have something that is not visible, but the neural network is making up stuff that actually is very sensible. Sometimes it's eerily good, and you have to you're wondering this is in the training set. And actually in the limit, you can imagine the neural net has enough parameters to potentially remember Earth. So in the limit, it could actually give you the correct answer, and it's kind of like an HD map baked into the weights of the neural net.
Yeah.
I have a question about the design of the Tesla bot. Specifically, how important is it to maintain that humanoid form? To build hands with 5 fingers that also respects the weight limits could be quite challenging. You might have to use cable driven, and then that also causes all kinds of issues.
I mean, this is just going to be bot version 1. I mean, we'll see. So it needs to be able to do things that people do, and you know, be a generalized kind of humanoid robot. I mean, you could potentially have it give it like, you know, 2 fingers and a thumb or something like that. You know, for now we'll give it 5 fingers and see if that works out okay. Probably will. It doesn't need to be like, have like incredible grip strength, but it needs to be able to work with tools, and carry a bag, that kind of thing.
Hi, thanks a lot for the presentation. So an old professor of mine told me that the thing he disliked a lot about his Tesla was that the autopilot UX didn't really inspire much confidence in the system, especially when like objects are spinning, classifications are flickering. I was wondering, even if you have a good self-driving system, how are you working on convincing Tesla owners, other road users, and just the general public that your system is safe and reliable?
Well, I think that's the cars. A while back, cars used to spin. They don't spin anymore. Not in. If you've seen the FSD beta videos, they're pretty solid, and they will be getting more solid.
Yeah, as you add more and more data and train these multi-cam video networks, like these are pretty recent, actually, just like a few months old, and it's still improving. It's not a done product, and in our minds we can clearly see how this is just going to be like perfect vector space, because why not? All the information is there in the videos. It should produce it given lots of data and good architectures, and this is just an intermediate point in that timeline.
I mean, it's clearly headed to way better than a human, without question.
Oh, hi, here. I was wondering if you could talk a little bit about the short to medium term economics of the bot. I guess I understand the long-term vision of replacing physical labor, but I also think repetitive, dangerous, and boring tasks tend to not be so highly compensated. And so I just don't see how to reproduce the, start with a supercar and then break into like the lower end of the market. How do you do that for a robot humanoid?
Well, I guess you'll just have to see.
Hello. Hi. I was curious to know how the car AI prioritizes occupant safety versus pedestrian safety, and what thought process goes into like deciding how to bake this into the AI.
Well, I mean, the thing to appreciate is that from the computer standpoint, everything is moving slowly. So, to a human, things are moving fast. To the computer, they are not moving fast. So I think this is, in reality, somewhat of a false dichotomy. Not that it will never happen, but it will be very rare. If you think it was like, going the other direction, like rendering, with full ray tracing, neural net enhanced graphics on something like Cyberpunk or any advanced video game, doing 60 frames a second, perfectly rendered. Like, how long would it take a person to even render one frame, and without any mistakes? Can't be done. I mean, it would take like a month just to render one frame out of 60 in a second in a video game. It's computers are fast and humans are slow. I mean, for example, on the rocket side, you cannot steer the rocket to orbit. We actually hooked up a joystick to see if anyone could steer the rocket to orbit, but you need to react at roughly 6-7 hertz. People can't do it. Not even now that's pretty low, We're talking more like aiming for like 30 hertz type of thing.
Hi, over here. With hardware 3, there's been lots of speculation that with larger nets, it's hitting the limits of what it can provide. How much headroom has the extended compute modes provided, and at what point would hardware 4 be required, if at all?
Well, I'm confident that hardware 3 or the full self-driving computer 1 will be able to achieve full self-driving at a safety level much greater than a human, probably, I don't know, at least 200 or 300% better than a human. Then obviously there will be a future hardware 4 or full self-driving computer 2, which we'll probably introduce with the Cybertruck, so maybe in about a year or so. that is probably, well, that'll be about 4 times more capable, roughly. But it's really just going to be, like, can we take it from, say, for argument's sake, 300% safer than a person to 1,000% safer? Just like there are people on the road who, with varying driving abilities, but we still let people drive. You don't have to be the world's best driver to be on the road. So, as we see. So, yeah. You guys want to say anything? All right.
So are you worried at all, since you don't have any depth sensors on the car, that people might try like adversarial attacks, like printed out photos or something to try to trick the RGB neural network?
Yeah, like what? Pull some like Wile E. Coyote stuff, like paint the tunnel on the wall. It's like, oops. We haven't really seen much of that. I mean, for sure, like right now, if you, most likely, if you had like a T-shirt with a T-shirt with like a stop sign on it, which I actually have a T-shirt with a stop sign on it, and then you like flash the car, it will stop. I proved that. But we can obviously, as we see these adversarial attacks, then we can train the cars to, notice that, well, it's actually a person wearing a T-shirt with a stop sign on it, so it's probably not a real stop sign. Yeah.
Hi, my question is about the prediction and the planning. I'm curious, how do you incorporate uncertainty into your planning algorithms? Do you just basically assume, you mentioned that you run the autopilot for all of the other cars on the road. Do you assume that they're all going to follow those rules, or are you accounting for the possibility that, well, they might be bad drivers, for example?
Yeah, we do account for multimodal futures. It's not that we just choose one. We account for, okay, this person can actually do many things. And we use their actual physics and kinematics to make sure that they're not doing a thing that would interfere with us before we act. So if there's any uncertainty, we are conservative and then would yield to them. Of course, there's a limit to this, because if you're too conservative, then it's probably not practical. So at some point, we have to assert. And even then, we make sure that the other person can yield to us and act sensibly.
I should say, like before we introduce something into the fleet, we will run it in shadow mode, and we'll see what would this neural net, for example, have done in this particular situation. And then effectively, the drivers are training the net. So if the neural net would have controlled and say veered right, but the person actually went left, and it's like, oh, there was a difference. Why was there that difference?
Yeah, and secondly,
So
we also...
all the human drivers are essentially training the neural net as to what is the correct course of action. Assuming it doesn't then end up in a crash, it doesn't count in that case.
Yeah, and secondly, we have various estimates of uncertainty like flicker, and when we observe this, we actually say if you're not able to see something, we actually slow down the car to be, again, safe and get more information before acting. Yeah, we don't want to be brazen and just go into something that we don't know about. We only go into places where we know about.
Yeah, yeah. It should be like aspirationally, the car should be the less it knows, the slower it goes.
Yeah.
That's just
not true at some point, but now it's
should be speed proportionate to confidence.
Thanks for the presentation. So I am curious, appreciate the fact that the FSD is improving, but if you have the ability to improve one component along the AI stack that presented today, whether it is simulation, data collections, planning and control, etc., which one, in your opinion, is going to have the biggest impact for the performance of the full self-driving system?
It's really the area under the curve of these like multiple points, and if you improve anything, it should improve the area.
I mean, the short term, it's arguably, we need all of the nets to be surround video. And so we still have some legacy. This is very short term, obviously we're fixing it fast, but there's still some nets that are not using surround video. And ideally that all use surround video. Yeah, Mary, yeah.
I think a lot of puzzle pieces are there for success. We just need more strong people to also just help us make it work.
Yeah, that is the actual bottleneck.
So that is the actual bottleneck, I would say, and really one of the reasons that we are putting on this event.
Exactly, well said, Andre, that there's just a tremendous amount of work to do to make it work. So that's why we need talented people to join and solve the problem.
Thank you for the great presentation. Lots of my questions answered. But one thing is, when imagine that now you have a large amount of data, even unnecessary. How do you consider that? Like there is a forgetting problem in neural networks. Like how are you considering those aspects? And also another one, are you considering an online learning or continuous learning, so that maybe each driver can have their version of self-driving software?
I think I know the literature that you're referring to. That's not some of the problems that we've seen, and we haven't done too much continuous learning. We trained the system once, we fine-tuned a few times. That sort of goes into the car. We need something stable that we can evaluate extensively, and then we think that that's good, and that goes into cars. So we don't do too much learning on spot or continuous learning, and don't face the forgetting problem.
But there will be settings that you can say, like, if you are you typically a conservative driver, or do you want to drive fast or slow? You know, it's like I'm late for the airport. Could you go faster than, basically the kind of instructions you'd give to your Uber driver. It's like I'm late for the flight, please hurry, or take it easy, or whatever your style is. So let's take a few more questions here. And then we'll call it a day.
All right. So as our models have become more and more capable, and I guess you're deploying these models into the real world, one thing I guess that's possible is for AI to become more, I guess, misaligned with what humans desire. So I guess, is that something that you guys are worried about as you guys deploy more and more robots? Or do you guys we'll solve that problem when we get there?
Yeah, I think that we should be worried about AI. Now, what we're trying to do here is, I'd say, narrow AI. We're pretty narrow, just make the car drive better than a human. And then have the humanoid robot be able to do basic stuff. So at the point at which you sort of start to get to superhuman intelligence, I don't know, all bets are off. But and that's that'll probably happen. But what we're trying to do here at Tesla is make useful AI that people love and is unequivocally good. That's our, we'll try to aim for that. Okay, maybe one more question.
Hi, my question is about the camera sensor. In the beginning of the talk, you had mentioned about building a synthetic animal. And if you think about it, a camera is a very poor approximation of a human eye. And a human eye does a lot more than take a sequence of frames. Have you looked into, there are these days are cameras like event cameras. Have you looked into them? Or are you looking into a more flexible camera design or building your own camera, for example?
Well, with Hardware 4, we will have a next generation camera. But I have to say that the current cameras, we have not reached the limit of the current cameras. And I'm confident we can achieve full self-driving with much higher safety than humans with the current cameras and current compute hardware. But it'd be good to be 1,000% better rather than 300% better. So we'll see continued evolution on all levels in pursuit of that goal. And I think in the future, people will look back and say, wow, I can't believe we had to drive these cars ourselves. It'll self-driving cars will just be just a normal, like self-driving elevators. Elevators used to have elevator operators. And there's someone there with a big relay switch operating the elevator, and then every now and then they'd get tired or, make a mistake and shear somebody in half. So now we made the elevators automatic, and you just go and you press the button, and you can be in a 100-story skyscraper and don't really worry about it. Just go in and press the button, and the elevator takes you where you want to go. But it used to be that all elevators were operated manually. It'll be the same thing like for cars. All cars will be automatic. And then, and electric, obviously. So there will still be some gasoline cars and some manual cars, just like there are still some horses. So, all right, well, thanks everyone for coming, and I hope you enjoyed the presentation, and thank you for the great questions. All right.
All right, hello. Here's my voice so you can turn down your mic. Okay, I guess it's over. Turn this music. Okay, they turned it off. I am exhausted. I don't have much to say. I'll probably wrap it up here. I think most people are probably going to leave anyway. But holy moly, that was pretty crazy. Let's just mute this so we can have it playing here. Wow. That was pretty crazy. Honestly, I don't know. People were talking about the robot. I really didn't think that was going to happen. It seems so far-fetched. So Joe, what's the robot for? It's for narrow tasks. He was saying boring things that people don't want to do and maybe things that are dangerous. So, I don't know, really repetitive, tedious tasks that you don't want to do, the robot will do. It's so far away. Do a video on it. I probably won't do a video on this just because I don't have that much time and nobody will watch it, to be totally honest. Bye for people that are leaving. See ya. Yeah, I'm just going to give my thoughts in a few minutes of that, and then we'll call it. But I'm totally blown away by the robot. I want one, obviously. It just seems... Yeah, vaporware to inspire engineers. Yeah, it seems so far off. It's not like this is going to be out next year or even in 2 years. But this is what Elon always does. He's always pushing. And like doing these things that people are like, oh, it's either impossible or it's really, really difficult. And he's always still pushing for them. He's like, no, we can do this. Let's do it. So with full self-driving, with the landing the rockets, with going to Mars, all of this stuff, he's just pushing and pushing. And he gets results. He's usually late. Plug and unplug superchargers. There you go. It's not dangerous, but it's tedious. So like if you have your full self-driving Tesla pull up, this robot might be standing at a supercharger, walks over and plugs it in. Like, sure, that's something it could do. No, I'm not going to bed. I still have a little bit of work to do, and then I'm going to bed. Anyway, yeah, so I think the robot's awesome. I want one. Now, price is what I'm really interested in, and somebody kind of asked, and Elon basically said, "Oh, you have to find out." Someone compared it to the model, how Tesla started with a really expensive car, and then had the Model S, and then had the Model 3. They're like, "Are you going to take that approach?" And he didn't give any indication. He said, "Well, you'll have to see." So, if this can really replace an employee, that's kind of the way I'm thinking about it. If it can replace a minimum wage employee, let's say minimum wage you make, I don't even know what it is now. Like, is it 12 an hour? So $24,000 a year or so. It's going to be at least that much, because then you're like, oh, of course I'm going to pay $24,000 one time for this robot rather than pay $24,000 a year for the rest of time to a person or the people I replace them with. So stop. Oh my gosh, you guys. So very cool. I think it's great. I mean, I'm trying to think of what around my house I would really want it to do. Like, take out the garbage. I actually don't mind taking out the garbage, because, you get outside. I like my house. It's nice to be out there. So that's not a big deal. I guess getting all the garbage ready and putting it into the garbage can would be sweet. Yeah, 24/7 working is great. You don't have to worry about this thing doesn't need brakes. It's not going to be smoking. It's not going to get sick. it doesn't need health insurance. You know, it probably needs some type of maintenance plan or something. And you have to pay to charge it. But yeah, raking the leaves, that's a great idea. Hate raking the leaves. Probably mowing the lawn. I don't know if they'd allow that because it's probably kind of dangerous. But yeah, raking the leaves is great. Zookeeper, shoveling snow. See, this is why I love chat, because you guys have all these ideas. Garden, yeah, picking weeds. Like, that seems like a really difficult task. But if the vision could be that good where it can distinguish weeds from, like, the plants you want to keep, boom, you know, it can do that. Daily car wash, build a deck. See, I don't think it'll be strong enough for that. They have the specs. I tweeted it. Where is it? Oh, no, that's not what I wanted to click. Oh, come on, dude. Here's the, let's see, if I put this here. Oh, hold on. Let me F11 this boy. We don't really need that anymore. Here's the specs here for you. We'll put this up. This didn't have the specs, but if you guys have them, you can share them. But yeah, so all these cool things. Walking the dog, like, come on, we should be walking the dog, right? We gotta be healthy. So that's the things. Replace my roof, yeah. Roadside man, there's a lot of things. I think some of these heavier things, it's not gonna be able to do, because he said it's 5'8". It weighs around 125 pounds. It'll only go 5 miles an hour. And let me see if I can. I go back here. Let me see if I can find the robot part here. Before the engineers come out. Oh man, I guess these guys talked for a while. There we go. Oh, there we go, right here. So 5'8". It can only carry 45 pounds. So that's like a tire on the wheel could be around. It should be less than that, but some tires and wheels, like on the Model X, the bigger, are probably heavier than that. Highly overpriced Ring doorbell. You just have it standing outside. Flip people off. Come on. Just have it standing outside of your front door. It's so stupid. Oh my gosh. It can deadlift 150 pounds. Arm extended, only 10 pounds. So holding something like this extended, it can only hold 10 pounds. So it's not going to be that powerful. I'm tired. Max speed 5 miles per hour, so you can outrun it. That's what he was saying. That's so funny. So it doesn't come kill you. You can just run away. Probably if you have a hover round scooter, you can't get away. I don't know. Those things probably go over 5 miles an hour. So it only weighs 125 pounds. And he said, hopefully you can overpower it. Most people, like, if it's like trying to, attack you, you should be able to just, So give it a gun, 24/7 security. So this is so funny. Oh, this is so you guys are hilarious. Oh my gosh. So deadlift 150 pounds. So like it can pick up something and maybe just set it down higher up or something for you. But arm extended 10 pounds is really not that much weight. Like, okay, the dog food gets delivered, like let's say you get the dog food, comes to your house. Carrying 45 pounds. So you have a 20-pound bag of dog food or a 40-pound bag of dog food. It could pick it up, like hold it here or something, and then it could walk and then just like drop it or set it down. It could not take a 40-pound or even a 20-pound bag of dog food and put it on a shelf. It can't extend its arms like that. So, how tall? It's 5'8". I have it up on the. Oh, sorry. I'm so stupid. Let me minimize myself. I'm sorry. There you go. There's all the specs right there. So yeah, world built by humans for humans. So it's got to be human-y, like friendly, and eliminates dangerous, repetitive, boring tasks. So that's what it's for. Writes parking tickets. There you go. Care for elderly. Yeah, like that's perfect. Care for elderly, like somebody who's not very mobile. It could go to the fridge and get you water. It could get water out of the sink. I mean, those applications are huge. So this thing, like just think theoretically, I think this is far off, in my opinion. I don't know anything, so maybe I'm totally wrong and stupid, and this comes out in 2 years. But I think this is like a 5 years away thing, where this actually comes out. Yeah, clean your car. But theoretically, all these applications like are stop. UPS delivery to the door. Yep. The robot needs the stop sign T-shirt. Oh my gosh, you guys are so neat. These ideas are so funny. Sell supercharger adapters. Okay. Okay. So that's sweet. And then I want to talk about hardware 4. He mentioned He said coming in about a year with Cybertruck, which makes me think Cybertruck's about a year away. So, you know, that's a little disappointing, but that's the way it is. He said new cameras. Stop, you guys. New cameras are coming with hardware 4. So, yeah, that's really good. Yeah. So, okay, cool. That's it. I have some work to get done before I go to bed. I wanted to go to bed early tonight, but obviously that's not happening. So, anyway, thank you so much for hanging out, everybody. That was like way too fun. This is one of the best events so far. I mean, yeah, Cybertruck was the best event. This is close though. This was so fun. So, all right. I hope you guys have a good night. Keep talking here for a bit, and I will see you around. You can comment on this if it goes live or whatever. So, all right. Have a good night, everybody. Bye bye.